Okay, let's start our tour of electricity and magnetism by making a comparison of gravity and electrostatics. Now, if you're one of my students, don't worry about anything that is in the first column because it's going to be later in the course when we start talking about what gravity is. But I think that you're more familiar with what gravity is, and so I wanted to compare gravity with electrostatics. So what is it that causes gravity? It's going to be the mass m of an object. And so, for example, the Earth is going to have a mass. And then if you take another mass up here and you let go of it, it's going to be attracted to the Earth. And so that's going to be gravity. So what is it that's going to be causing electrostatics? And that's going to be electrical charges. And we're going to abbreviate electrical charge with the letter Q. And then its official metric unit is going to be called the coulomb, which we're going to abbreviate with a C. Now, a coulomb is a very, very large number. So, for example, the charge on the electron is 1.6 times 10 to the negative 19th coulombs. So that, which is not surprising because in our previous lesson we talked about the mass of a typical atom and it was incredibly small, so it's not surprising that the electrical charge on the parts of the atom is also going to be very, very small. So that a coulomb is going to be the official metric unit for electrical charge. Now there are two kinds of electrical charge. You have positive electrical charges, which are going to be associated with protons, and then you had negative electrical charges, which were associated with the electrons. Now notice when it goes to gravity, though, that there's only one kind of mass, and mass is always attractive. But what we're going to find out is that with electricity, since there are two kinds of electrical charge, electrical forces can attract and electrical forces can push things away. All right, what does conservation of mass mean? So that means you can't create or destroy mass, at least on a classical level. So for example, let's say that this thing has a mass of 10 grams. All right, now I'm going to break it apart so that I've got 1 gram over here. How many grams would this thing over here have to be? It would have to be 9 grams. So whatever mass you start with has to equal whatever mass that you end with. So that's conservation of mass. Now, having said that, later in the videos, we're going to talk about nuclear processes, and we're going to talk about Albert Einstein. And one of the things that he came up with was a formula that related the total energy of a system to the mass of a system and then the speed of light of the system. And so he found out that mass could be turned into energy and energy could be turned back into mass. And so, to be precise, conservation of mass means we need to take energy into account, and it's actually conservation of energy mass. All right, but let that ooze out of your head. So we're just going to do classical gravity here, and we're going to say that you can't create or destroy mass. So what would conservation of charge mean? It means you can't create or destroy electrical charges. So let's say that you have an atom that is going to have, let's say, 2 protons in its nucleus, and then let's say it's electrically neutral, so it's going to have 2 electrons that are in orbit around that nucleus. So notice you got +2 and -2. When you put them together, you get 0. Now, what would happen if you took one of these electrons, one of these negative electrons away? right? Could you predict, using conservation of electrical charge, what would now be the charge on this thing here? So it was electrically neutral. We removed a negative electrical charge. And so what is going to be left over? So let me put that over here. Negative electrical charge. So we're going to remove that. So this thing now is going to have a net charge of +1, because this thing over here has a net charge of -1. So it's conservation of electrical charge. You can't create it and you can't destroy it. All right, now let's talk about electrical forces and gravitational forces. So let's first look at the gravitational force, and it says now you're going to have two masses, and so we could call this one M1 and we could call this one M2, and they're going to be separated by a distance r. So r is going to be the distance from this mass to this mass down here, and then there's going to be a formula for the force of gravity that is going to be attracting those two. So a force is going to be given by the letter F. Okay, a force is a push or a pull. When you push on a refrigerator, you're exerting a force on it. When you are playing tug of war and you're pulling on the rope, you're exerting a force on it. So a force is a push or a pull. The official metric unit that goes with force is a Newton. So that's the official metric unit for force. And there are gravitational forces. So if I take this thing and I let it go, this thing is experiencing a force which is pulling it down. So similarly, we could have an electrical force. So in the case of gravity, so let me get rid of this. In the case of gravity, we'll say the gravitational force is going to be equal to minus, and the minus sign just means that gravity pulls inwards. And then there's going to be a constant of nature that goes with it called the gravitational constant, which we don't care about, okay? It's important, but we just don't care that much about it. And then it's going to be mass number 1 multiplied by mass number 2, and then divided by the distance between them squared. So let's compare that to the electrical force. So this time it's going to be the force of electricity is going to be equal to a fundamental constant, which we say is going to be K, and this one's it's called the electrical constant, and I give it to you there, but don't worry about it, okay? It is a fundamental constant, and then instead of masses, we're going to use charges. Mass causes gravity, electrical charge Q causes electricity. So this time we're going to have Q1 and then Q2, and then we're going to divide it by R squared. So notice how similar the two formulas are. Now you might be wondering, well, this one down here has a negative sign, but it's going to depend on the charges. So if you've got a plus charge and a negative charge, they're going to attract each other. But if you have a plus charge and a plus charge, they're going to repel. Or if you have a minus charge and a minus charge, they're going to repel. Okay, so that's very important. You should know that for the exam, that like charges repel and unlike charges attract. So I've got a little simulation here that I would like for you to take a look at. And so this is PhET. So pause me if necessary, and you're going to go to the internet, just type in the word PhET, P-H-E-T, and then type in Coulomb's law, and it should take you right to this simulation. So find that simulation for me. All right. So what I want to do with this simulation is verify this formula right here. So in lab, we're actually going to be able to come up with a formula like this just by using the simulation. But I just want you to see some general things about it. So one of the things you can do is you can grab the balls and you can move them back and forth. So as you move these balls back and forth, each ball is going to have a certain amount of electrical charge on it. Now you can control the amount of electrical charge down here. So you've got the charge on ball number 1, and then you got the charge on ball number 2. And so by using, you can either use the slider or you can use these things, and you can change the amount of charge on them. Okay? And then up at the top, I want you to look, here is the force on charge number 2 caused by charge number 1. And then down here, this is the force on charge 1 caused by charge number 2. And so take a look at, all right, so let's go ahead and give it some electrical charge there. All right, and then look at this number here, and then look at this number here, and what do you notice? The two numbers are identical. So the force on one object caused by the other object is the exact same as the reverse of it. So this is going to be an example of Newton's third law of motion. For every action, there's an equal and opposite reaction. Now for us, we don't really care about that, okay? So just concentrate on one of the numbers. Now what I want you to do is I want you to decrease the amount of charge on this charge right here. And before you do it, I hope you haven't done it yet. So before you do it, I want you to predict what's going to happen to this number up here if you decrease the charge on this ball. Okay, did you make a prediction? So you're going to have one of three choices. The force is either going to go up, the force is going to go down, or the force is going to stay the same. Okay, make your prediction. All right, so now go ahead and do it. So decrease the amount of charge on this ball, and then you notice that it decreased. All right, now how could we have predicted that just based on the formula here? So we're going to decrease Q2, and we want to see what happens to F over here. Okay, so let's say that we decrease it by 1/2. So we have 1/2 the amount of charge now. What would that do to this thing over here? So remember, whatever you do to one side of an equation, you got to do to the other side of the equation. So that would mean you'd have 1/2 the amount of force. So notice if you've got variables and they're on the top part of a formula, if you decrease them, it decreases it. If you increase it, it increases it. So we call that a directly proportional formula if the variables are on the top part of a fraction. All right, now what we're going to do is I want you to, this time, you're going to make a prediction, and what I want you to do is to increase the distance between the two balls, and I want you to make a prediction as to what do you think is going to happen to the force if you increase the distance between them. Okay, did you do it? All right. So this time, if we increase the force, increase the distance between them, it decreased the force. Now, how's that possible? Okay, Now we're changing the R, and the R is in the bottom part of a fraction, so that if you make this bigger, it has to make this over here smaller. And you can see that just by, with your calculator, you could take 1 divided by 1, which is 1, but you could take 1 divided by 10, and then that's 0.1. So the bigger the number in the bottom part of a fraction, the smaller the number that comes out. So this is called an inversely proportional variable because it's on the bottom part of the fraction. So I just wanted you to see this little simulation, and that it does verify this formula here. And so now, let me get rid of this, and let me show you an example of a type of question that could be on the exam. Now you'll notice that this formula has a yellow box around it. So that means the kind of question I'm going to ask you is a conceptual question. So let's take a look at a conceptual question here. Charge number 1 is located a certain distance from charge number 2, and it feels an electrical force. If charge number 1 is moved 5 times further away, what will be the new force of electricity? Okay, so we're going to use this formula here, and instead of R, we're going to put in a 5. But remember, the 5 has to be squared. So 5 times 5 is 25. So therefore, the new force of electricity is going to be 1/25 of what it used to be, or you could say 25 times weaker. So either of those two answers would be correct on the exam. Okay, so that's an example of a type of question that could be on the exam. I tell you that the distance changes by this much, and you tell me what's that going to do to the force of electricity. Now, if you want, if you actually knew what the charges were in coulombs, and then if you knew the distance between them in meters, and you know the value of K, okay, because if we go back here, we know the value of K is 9 times 10 to the 9th. We could put all of that into this formula, and we could actually calculate the force of electricity in newtons. We're not going to do that. So I just want you to be able to do it conceptually, and then if you go on to take a higher physics course, you would actually take numbers, put it into the formula, and then calculate the actual force of electricity. Okay, let's take a break. When we come back, we're going to talk about what the electric field is.